Okay. Wait a second, what is this number? Number bros? No, definitely not. Wait. I guess it makes sense. 226, yeah. What does that number mean? Sure. Cool. Okay. Seems like unnecessary right now. Wait, why is this all commented out? What? Oh, sure. Okay. Program outputs the image to standard output, so leave that alone. Instead, write to the logging output stream. It's .h, not .hpp. It's just kind of weird. Header guards. See, I hate that. Well, E, I'm assuming elements, but I guess it kind of makes sense. But I still don't like it. I guess it is. It's easier to type though. Harder to read, but a Vec 3 class isn't the most complicated thing. It is a little bit, a little bit more verbose, and you have component instead of E. I will say that. See, that is in a way kind of harder to read, isn't it? Kind of. In a weird way, man. No, so it's just a negative operator, not a minus operator. Right? You're turning a negative version of the vector. It kind of does make it a little easier to read to just do E, because it gets really verbose. You have component everywhere. I guess. Now we're indexing into it, right? Or what's the difference between these two? Man. What's the... How do you copy without using the fucking mouse, dude? So if you index into a const object, it'll return a const, so you can't modify it? What? To do a normal vector, you do it, it'll use a non-const version. Leave the const, okay, so it's just based on that. That makes sense. And we also have a plus equals an increment operator. We're saying if you're saying the given vector plus equals a different one, it would just say our vectors, each element plus that the other vector's element of the same, position. X plus x, y plus z, and then return this dereference, or return a reference to this object. If you're dereferencing a pointer, why is it by reference? How can returning this, aka this, a dereferenced pointer, be returned by reference? Example, vec3 reference vector plus equals const vec3 blah blah blah, return this. Oh, I guess, yeah, I guess because the reference is, it's like a pointer, but it's not a pointer. You only return something, an object itself, not a pointer, by reference. I guess it kind of makes sense. And this is similar, except this is by like a scalar instead of an actual other vector. Sure, makes sense. Makes sense. Do we have a division one? The length of a vector is, we actually used length squared, so let's do that first. Length squared because that goes back to the what's it called, magnitude? Yeah, right. The length of a vector is a square root of this, so we say, okay, well, what is the length? The length is the square root of that, so length squared would be this without the square root, which is all the elements squared by themselves summed. So we have that, and then this is simpler by saying the square root of that. Now, is this length squared used anywhere else? Because otherwise that seems like a really pointlessly roundabout way of doing it. Like, why not just say like return the square root of this? You know what I mean? Like, why are we making a whole other different method? And this is also interesting. You're saying you could take the current object, and we're using so that okay. So this division operator, overloaded operator, makes use of the previously implemented multiplication operator overloaded operator by doing times 1 over t, because you know a number divided by 2 equals 4. This is the same as 8 times 1 over 2, right? 8 times a half. Yeah. Okay. It's still weird that that was a whole extra function, but it makes sense. Doesn't matter. It makes sense what it's doing, at least, if not the motivation for it. Okay. So let's see. Length squared. I think this is just for printing out the object, right? Never really understood the syntax for these, but I understand what it's doing at least. I understand the purpose of it. Curious why these are inline though. And adding 2 vectors. So again, U and V is another thing like M and N, I and J. I'm not a fan of that. Let's call it V1 and V2. So we're making a new vector based on these. We'll do a similar thing for minus. Okay, and for multiplication, this is a vector times a vector, then this is a double times a vector. Although vector multiplication is not necessarily what you think. Although in this case it is. Let's forget the keybinds for this. Control E and Y. Yeah, that's right, that's right. Okay. So this one is vector times a scalar. Which is just going to be the same thing. It's just a way to have the order not matter. Because if you didn't have this function, you'd think, oh, we already have the logic. But right here, well, in the code, if you were to say, you know, if you have some vector times some number, it would say, we don't know how to do that. So this is just is putting the arguments in a different order here. Similar to above, just using the multiplication to do division by flipping one of the things. Now I have the dot product, okay, and the cross product. Yeah, because the dot product is the one that returns the like a single number, like a scalar. Whereas a cross product is one with the really weird rule that you kind of just need to memorize the order of it. Man, every time. Which makes it very painful to type. So it's y times z and z times y, and then it's like the a times z. No, well, yeah, it is. It's z times a though. Well, it doesn't matter. It does it. And then x and y. And then the unit vector, which unit vector is just like a fancy way of saying unit vector is just a fancy way of saying scale down the vector, or scale up, I guess, technically. So that the overall length is 1. It's like, it's not that. It always seems a lot more complicated than it actually is. Now, why are all these inline? What? Oh, sure. Oops. Okay, we also want color utility functions. Pixel color, is that a... Oh, it's a thing passed in. Oh, sure. Duh. Just type that. Translate. Okay, so map them a little bit. 0, 1. Values to the weight range. Okay. Oh, did I ever add the endif to the other one? There's supposed to be an endif here? I assume so, yeah. Why is this here, though? Is there not supposed to be one? Oh, these are not supposed to be in the class. I'm guessing. Yeah, okay. And then add the endif. Okay. I can change main to use both of these. I don't want to rename this one. Cool. We can choose our now we can change our main to use both of these. Okay. Cool. Instead of doing all of this, I don't like that. I still like doing it this way. There's any reason not to do it that way. You're making you're making a vec3 a color. And then we want to write the color. Instead of doing it like this, right? Let's see how many errors we get there. Vec3, yeah. Color does not name a type, yeah. Cool. Let's just added some utility functions to clean the code a little bit. Makes sense, makes sense. And now the kind of mathy stuff. A little bit. Okay. The only thing that all ray tracers have is a ray class and a computation of what color is seen along a ray. Let's think of array as a function. P of t equals a plus t times b. Your p is a 3D position along a line in 3D. A is the ray origin and B is the ray direction. The ray perimeter T is a real number. Plug in a different T and P moves the point along the ray. The negative values go anywhere, go either direction. Oh, anywhere on the 3D line. For positive T, you only get parts from B, A, and this is what is often called a half line or array. Well, I'm confused at that. So A is the ray origin. Interesting. Sure. You can represent the idea of array as a class and represent the... What have I ever got? Did I ever get this far? I must have gotten this far, right? Ooh, did I get that far? I definitely got that rendered at one point. Maybe that. Definitely not that though. Okay. Just remember how far I got before. For positive T, you get only the parts in front of A, and this is what is often called, okay. Represent with a class. Represent the function P sub T as a function that we'll call array at. Okay, another class, another file. array has both an origin and direction. The array is kind of just a vector, like a... Right? It's kind of just a vector, not like a XYZ 3D. I don't know, but they are kind of the same, aren't they? This doesn't really made sense about calling things vectors. Like, a vector kind of just means a collection of 3 points. Now, often that means some sort of 3D point that has a direction and origin, but like, not. I don't know. It's never really made sense to me. It hasn't quite clicked yet that how that works, what that means. It's always so fun to me. Tutorials do things like this. They'll have all this code, all of this code, including things like overloaded operators, including things like already returning, like reference. Maybe it's because overload. I don't know. He doesn't feel the need to explain any of this code and what's happening here. Any of the math behind it, the reference to the, the reference type, return type being a reference, anything like that. But then down here, he's like, hey, by the way, here's what's going on here. It's just strange. Like a point's representing a static point in space, I guess. A vector is representing kind of the same thing, but just like with a tail, right? Like, I mean, literally in the code, the 0.3, object is literally the same thing. Oh god. It's literally the same thing. Like, you have, oops, no pen. Like, if you have a 0.3, it's a point somewhere in space with an X, Y, and Z. You have a vector though, it's a point somewhere in space, but really it's just a point that we point to that also has an X, Y, and Z, but it's thought of differently. It doesn't really make sense to me. Point's not different than a vector, but we think of it different as a vector. An array is not really different from a vector. We think of it as a vector, or we don't think of it as a vector. I don't know. It's kind of wacky. Ready to turn the corner and make a ray tracer at its core. A ray tracer sends rays through pixels and computes the color seen and the direction of those rays. All steps are calculate the ray from the eye through the pixel, determine which objects intersects with the ray, and compute a color for the closest intersection point. When first developing ray tracer, I always use a simple camera for getting the code up and running first. Okay. See, again, it's funny that things like this are explained so in depth, but other things are just not even touched on at all. Things that to me would seem less intuitive. Like this in and of itself, maybe it's because I already understand aspect ratio is a ratio between width and height. But this seems pretty intuitive. Like this, I mean, right here, it already says a 16:9 aspect ratio means that the ratio of image width to image height is 16:9. It's saying this is a ratio of height to width, or width to height. Put another way, give it an image width. Here's an example. For an example, here's this. It can be determined by its width to height. This is one of those things, though. Anyone, even people who have like such a well-known, popular, I guess, course or book like this, everyone will struggle with like the decision of where to have a lot of clarity and where to kind of not even be hand wavy, but just not really dive into any of the details at all. Probably a hard thing to determine, especially because once you have such a good understanding, like a good enough understanding to make something this in depth or this complicated or whatever, you kind of forget what needs to be explained and what doesn't. Viewport. The concept of viewport still kind of messes with me. I don't really get it. Also need to set up a virtual viewport through which to pass our scene rays. The viewport is a virtual rectangle in the 3D world which contains the grid of image pixel locations. If pixels are spaced the same distance horizontally as they are vertically, the viewport that bounds them will have the same aspect ratio as the rendered image. The distance between two adjacent pixels is called the pixel spacing, and the square pixels is the standard. Okay, I'm gonna be stopping here soon, so let's just get this code in. We don't have to, we can just kind of read through this and start back here next time. Okay. Where's the virtual thing? Start things off, we'll choose arbitrary viewport height of 2 and scale the viewport width to give us the desired aspect ratio. Here's a snippet of what this code will look like. We'll have our aspect ratio of our width, and then we'll calculate our height based on our aspect ratio. If our image height is negative, oh, sure. Viewport width less than 1 are okay since they are real valued. Oh, it's less than 1, not meaning negative, but meaning a decimal number. The image height was allowed to be real valued. Image integer, then it would be fine to use aspect ratio. First, I'm just running down to the nearest integer. Note that the aspect ratio is an ideal ratio. spacing out. Aspect ratio is an ideal ratio, which we approximate as best as possible with the integer-based ratio. What's over its height in order for. I feel like he just reiterated this. Point in 3D space from which all the scene rays will originate. This is also commonly referred to as high point. Okay. The vector from the camera center to the viewport, orthogonal to the viewport, sure. We'll initially set the distance between the viewport and the camera center point to be 1 unit. The distance is often referred to as the focal length. We'll also have the y-axis go. We'll also have the y-axis go up, the x-axis to the right, and the negative z-axis pointing the view direction. Right-handed coordinates. Okay,